Hello there, Mr. Sutton here, bringing you this AB Calculus 610 homework solutions on rate in, rate out. For this calculator-based free response problem, we have the tide removing sand from Sandy Point Beach, it's a nice name, at a rate modeled by this R function here, and a pumping station is adding sand to the beach at a rate modeled by the S function over here. And R and T and S of T both have units of cubic yards per hour of sand. And we're measuring this between times 0 and 6. And they're telling us at time 0 the beach has 2,500 cubic yards of sand. So for part A, we want to know how much sand the tide will remove from the beach during the 6-hour period with units of measure. Okay, so let's go ahead and take a look at this R function here. This is the removing function. This is the rate at which sand is being removed. So if we want to find the total sand removed, we just need to integrate this rate of change on the interval from 0 to 6. So here's our setup. Integral from 0 to 6 of R of t dt. And let's go into Desmos now, and let's clear all this out. Now while I'm in Desmos, I'm going to put both functions in there. So I have R of t, and that's going to be 2 plus 5 sine parentheses, fraction 4 pi t over 25. And now let me make another entry for S of t. I have a feeling I'm going to need to use this one as well at some point. Not on this problem though. So 15t plus over 1 plus 3t. And I don't necessarily need to graph either of those, so I'll deselect them, but I am going to use the R function. So I need the integral int from 0 to 6 of R of t dt. And that comes out to 31.816, and that's going to be cubic yards of sand. For part B, they want us to write an expression for y of t, which they're defining as the total yards, cubic yards of sand at time t. So for this we have three components. We have the sand that we're starting with, 2,500, plus the sand that we are pumping in. Now to find that sand, we need to do the integral from 0 to 6, actually 0 to t, and inside our function we're going to need a different variable, so we're going to call this s of x dx, the way we write this. And now, so we've got the amount that we started with, the amount that we're pumping in over the time from 0 to t. We also need the amount that the tide removes from 0 to t. So that's going to be the integral from 0 to t of r of x dx. And again, I need a different variable inside here versus the upper limit variable. Now you could just leave it this way, and that's fine. Or if you wanted, you could do s of x minus r of x dx inside one big integral, and that works just as well. For part C, they want us to find the rate at which the total amount of sand on the beach is changing at time 4. So the total rate of change is just going to be rate in minus rate out. So we can define y prime as s of t minus r of t. And then if we want to know what this is doing at time 4, we just need to do y prime of 4. So here's what this looks like on Desmos. So I'll get rid of this integral here. I'm going to define a new function, and I can't call it y prime because I haven't defined y, but I can just call it like lowercase y. So y of t equals, and we'll do s of t minus r of t. And now I just need to do, if I want to do y prime of 4, I'm going to do on Desmos just y of 4. And it's giving me issues here. Why is it giving me issues? Oh, probably because I'm using y. Desmos, it turns out, really doesn't like it when you use x and y as function names. So I'm going to change this to f of t. And now I'm going to call this f of 4. And now Desmos is perfectly happy to do that. So yeah, just don't use x or y for variable name, for function names. So this is negative 1.909 if I round it off. And it's the rate at which the sand is changing, so that's going to be cubic yards per hour. For the final boss battle of this free response question, we want to know for what time between 0 and 6 is the amount of sand at a minimum, and what is the minimum value. So to figure this out, we're going to need to find critical values of our sand amount function, which again was y of t. So we need to see where y prime of t equals 0. And I'm going to go back to Desmos to accomplish that. So remember that I defined this on Desmos as f of t, because it doesn't like y. And then we want this is defined between 0 and 6. Let me zoom in a little bit and see what my critical values are. So it looks like we don't actually touch the x-axis at all with that first little piece there. But if we go over here, it looks like we are crossing at about 5.11787. I'm going to copy that, and I'm going to store that value. I'm just going to call it A in Desmos and also on paper here. So this is our only critical value on the interval from 0 to 6. Is at about 5.1179, and that's in hours. So when I look for the minimum, I'm going to have to, there's a couple ways we could go about it. At some point, I'm going to have to plug some number into the y function. So I'm going to have to actually define the y function on Desmos in a minute so I can plug things into it. Now, what numbers am I plugging in? Well, you could just use the candidates test. We could plug in this critical value that we found, and we could also plug in the endpoints of 0 and 6 and just take the lowest value. Another way you could approach this problem, which I didn't do, but you could have, since there's only a single critical value and it's a local min because we're going from negative to positive on this derivative, you could put some wording in here to talk about that and then just have to plug in this one value. But let me show you exactly the way I did this here. So let me just methodically plug in the endpoints and the critical value. So y of 0, I actually don't even need to define that on the calculator to do y of 0. That's just the amount of sand at time 0, and that's 2,500. So we actually kind of knew that already. I also want to do y of a, though. For that, I'm going to need the 2,500 plus the integral from 0 to a of my y prime here. So let me do that on the calculator. So let me do 2,500 plus integral int 0 to a, and I actually have y prime defined as f right here, so I'm just going to do f of t dt, and that comes out to 2,492.369. So we'll take a look at that and compare it to some other values in a moment. And then let me also do y of 6. That's going to be 2,500 plus the integral from 0 to 6 of y prime. Now, since I've already entered most of this on the calculator, I'm just going to go back to my expression here, and I'm going to change this upper limit of a to a 6. That's actually a pretty easy change. And this is 2493.277. So let's look at these numbers closely. What's the minimum value? 2492.369 is the lowest out of these three, just by a little bit. So we see that our absolute min of 2492.369 cubic yards happens at A hours. This is the time that they wanted. This is the amount. On this calculator-based free response problem, on a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by this g of t function. And t is measured in hours, and the time is between 0 and 8 that this function applies. At the beginning of the workday, time 0, the plant has 500 tons of unprocessed gravel, and during the hours of operation from 0 to 8, we're processing gravel at a constant rate of 100 tons per hour. Okay, so part A on all this, they want us to just find g prime of 5 and then, using correct units, interpret this in the context of the problem. So the first piece of this g prime isn't too bad. We just have to plug g into our calculator and do g prime on there. Let me show you how I did that on mine. So I put my g function in there. So g of t, and then we got 90 plus 45 cosine parentheses, let's see, fraction t squared over 18, and there's my g function. Now I'm just going to do g prime, so g prime and then put 5 in there, just like they said, and that's going to be negative 24.588. That's great. So what did we actually just find here? So what this is saying, since I plugged in 5, this is happening at 5 hours into the hours of operation. What's happening at 5 hours? What's changing here? So G itself was the rate at which unprocessed gravel was arriving. So the rate at which unprocessed gravel is arriving, since this is the derivative of that rate, that's telling us that that rate itself is decreasing because this is negative. And it's decreasing at a rate of 24.588. And now we have to nail the units here. What units should we put on this? So whenever you take a derivative, you're always going to be dividing by the units of the input variable. The input variable in this case has hours for the units. So we're starting with the original units, which was, let's see here, they said tons per hour, and we're dividing that by hours. So this is going to be 24.588 tons per hour squared. For the next part of the problem, they want us to find the total amount of unprocessed gravel that arrives at the plant during the hours of operation on this workday. So we're not really thinking about this 500 tons that we started with. All we care about for this part of the problem is how much arrived after time 0 and until time 8. So since we have the rate of arrival, this g of t function, we just need to take the integral of that rate from 0 to 8. So this is all I'm putting down before I write my answer. Integral from 0 to 8 of g of t dt, because they gave us all that. Let me go back to Desmos. And I don't need this g prime of 5 anymore, but I do need int for integral 0 to 8. And then I'll just put in g of t dt. And that's going to be about 825.551. And that's going to be tons of gravel. For part C, they want to know if the amount of unprocessed gravel at the plant is increasing or decreasing at time 5 and show how we got that. So we've got two rates of change going on. We have the rate at which gravel is coming in, that's this g of t function. We have the rate at which it's going out, which is this constant function of 100. So really what we want to know is at the exact time, 5 hours, is g of t or this 100 going to give us the bigger value? Are we getting more in or more out? So let's find what g of 5 is. And again, we'll go to the calculator for that. So let me get rid of that integral. Let's just do g of 5. And that's about 98.141. And that's in units of tons per hour, if they wanted to know. So how does this compare to the rate at which gravel is being processed? Well, this is less than the 100 tons per hour that we're processing this at. So since we're getting less in than out, that means the amount of unprocessed gravel is decreasing at that time. For part D, they want to know the maximum amount of unprocessed gravel at the plant during the hours of operation with justification. So before I can really do much on this problem, I'm probably going to want to define a function to represent the unprocessed gravel. I'm going to call that u of t. So u of t is amount of unprocessed gravel. Now, we don't have an exact function for this just yet, but we can come up with a function for u prime of t, which we're going to need in order to figure out critical values and all that. So the rate at which the unprocessed gravel is changing is actually comprised of two components. We have the rate out, or the rate in rather, this g of t function is the rate in, and the rate out is this 100. So it's just going to be rate in minus rate out, which we can represent as g of t minus 100. And this is going to give us the rate at which the gravel is changing. So in order to figure out where this amount is maximized, we need to find critical values and probably also plug in some endpoints as well. But let's get our critical values. So I'm going to set u prime equal to 0. And on Desmos, I'm going to figure out where we're crossing the x-axis for this. So back to Desmos we go. And for this, I'm going to actually call this little u of t. I can't use primes on Desmos unless I've already defined the original function. So if I'm starting with a derivative, I need to call it something else. And I'm going to let this equal, again, g of t minus 100. So now I need to find out where this crosses the x-axis between 0 and 8. Let me adjust my window here. I'm going to go from, let's say, -1 to 9. That'll give me a little bit more than the window I need. And I see one crossing here, and that's probably all I really need for this problem, but I am kind of curious as to what the shape of this thing is. So let me just make my y values a little bit bigger so I can see all of this. So if I make it 80, I can see a little bit more of the function here. And let's see here. Let me actually deselect g of t. So now I've just got u of t. So there we go. If I click on this now, we're crossing, it looks like, at about 4.923. And I'm actually going to copy that, and I'm going to call that A. I'm going to store that as A, just so I can easily use it later on. So I'm going to say let t, so this happens at time A equals 4.9235. Now I can also use A in my justification. I don't want to keep rewriting this number. So at this point, I'm going to do the candidates test, basically plug in the critical values, of which there's only one, and also plug in the endpoints of 0 and 8. And we'll just take the highest value. Now this is one way to do it. Another way, since there's only a single critical value, and because the derivative is changing positive to negative, it's a local maximum. That tells us actually that this is going to be the absolute maximum. And there's ways you could justify that this is the absolute max, and then you could just plug A in and figure out the value from that. But I'm going to do the candidates test because, well, why not? So let's do u of 0 first. That's the amount at time 0. We don't need to do anything fancy for that because they told us we started with 500 tons of unprocessed gravel. So u of 0 is just 500. Now to get u of these other values, I'm going to need to do 500 plus the integral of this u prime here from 0 to whatever time I'm talking about. So if I want to do u of this a value, this a time here, that's going to be 500 plus the integral from 0 to a of u prime of t dt. So let me go back to the calculator to actually do this, and let me move this so I can actually see what I'm doing now. So let me do 500 plus integral, int, from 0 to a of u, little u is what I called my u prime, little u of t dt. And that's about 635.376. Now I also need to test the other endpoint if I'm doing candidates test. So that other endpoint is 8. So that's going to be 500 plus the integral from 0 to 8 of u prime. Let me go back to Desmos, and I'm just going to replace this a with an 8. And that's 525.551. So my three values, 500, 635, 525, clearly the 635.376 is our maximum value, so that's how many tons we have at most during this time interval. For this calculator-based free response problem, we've got a lot going on here. The amount of water in a storage tank in gallons is modeled by a continuous function on the time interval 0 to 7, where t is measured in hours. In this model, the rates are given as follows. So we have a rate that water is entering the tank, given by this weird f of t function, which has polynomials, trig functions, radicals, a little bit of everything, from 0 to 7. And that's in gallons per hour. We also have water leaving the tank, and that's given by this piecewise function, which is kind of simpler. Between times 0 and 3, water is leaving the tank at 250 gallons per hour, and then, I mean, something must have happened to bust this thing open, because 2,000 gallons per hour is what's happening between 3 and 7. Now we're given the graphs of f and g, which was nice of them, and they told us that these intersect at 1.617, which is right here, and this must be the 5.076 they're talking about. And then we're also told, and this will be important later on, that at time zero, the amount of water in the tank is 5,000 gallons. So a number of questions they're asking. The first is, how many gallons of water enter the tank during the interval from 0 to 7? So that relies entirely on this first rate, the f of t function. So to figure this out, since we know the rate at which water is entering, we just need to take the integral of f of t on the interval from 0 to 7. So I'm just going to write integral 0 to 7 f of t dt, and I'm going to go to the calculator now and just plug that right in. So here I am on the calculator. Let me put the f function in here. So that's going to be 100 t squared times the sine of, I need square root of t, and let's get out of there. So let me do now integral int 0 to 7 and f of t dt, and that comes out to 8,263.807, and that's going to be gallons of water. And they said round it off to the nearest gallon, so that does round to 64 there. For part B, on the interval 0 to 7, they want to know the time intervals during which the amount of water in the tank is decreasing, with a reason for this. So we have the rate in, f of t, we have the rate out, g of t, and they're both graphed here. F is the curvy line here, and g is these two horizontal lines. Basically, we're just asking, if we want to know when the amount of water is decreasing, we want to know when the rate out, g of t, is greater than the rate in, f of t. So we're just going to look at the graph here for all the places where this is happening. So initially when we start out, g of t is greater, higher than f of t, and that continues from 0 until this 1.617 spot right here. And then after that, f of t is higher, so the water's going in faster than it's going out, and that continues until we get to 3. At 3, we leap up here to a much higher rate of water going out, and g of t is again greater than f of t, all the way from 3 until this 5.076 spot. After that, f of t kind of takes over again, and we've got more water going in than going out. So since g of t is greater than f of t on these intervals, that's telling us that the amount of water is decreasing on these intervals. For this final boss battle, part C of this question, they want to know at what time the water is greatest in the tank, and also to the nearest gallon how much water there actually is at that time. Alright, so if we're going to be maximizing the amount of water, let's write a function that will describe that amount of water. I'm going to call that w of t. That'll be the water amount. We're defining it now. And I'm not going to define exactly what w of t is formulaically yet, but in order to figure out the maximum value, I'm going to need to know a little bit about the derivative of w so I can talk about critical values. So w prime of t, the rate of change of water, is going to be the rate in, f, minus the rate out, g. So there's my w prime, and I'm trying to find out some critical values for this. Now I'm going to be a little bit more specific about my critical values because there's a lot of them that are happening here. Basically anywhere that this thing is either undefined or equals 0. I mean, if you're counting undefined or 0, well, f of t and g of t have the same value at these two intersection spots, and because g is undefined at 3, the whole function is undefined there. So that's potentially 3 critical values. Now, if I'm looking to maximize the amount of water, the only critical values that I really need to test are ones that are going to be local maxes, places where w prime is changing from positive to negative. So just looking at the graph and finding those, I'm basically looking for places where we're going from f being higher to f being lower than g of t. Because when f is higher, this comes out positive. When f is lower, this comes out negative. So when we start off, F is lower. F doesn't get higher until we get past this 1.617 spot, and then F is higher until we get to 3. At 3, G becomes higher again, and this W prime is going to become negative at this 3 spot. And that's the only place that that happens. At this other changeover, we're going from negative to positive again in terms of this difference. So I'm going to write that W prime of t changes positive to negative at time equals 3 only. And that gets me off the hook of having to test out these other critical values that there's no way these could be the local max, the absolute max, because they're local mins. So now we only have to test out what W of t is at 3 and also at our endpoints 0 and 7. Okay, well, 0 is kind of easy. That's just the amount of water in the tank at time 0, and that's 5,000. So W of 0 is 5,000. That was given in the problem. Now these other ones are a little trickier. In order to find W of 3, I need to take the 5,000 and add to that the total change in the water from time 0 to 3. So I've got 5,000 plus, and now I'm going to need an integral from 0 to 3. What should I put in there? Well, I'm going to have W prime. But I can't really just write W prime because G changes halfway through this problem. So I'm going to have to be a little more specific. So I'm going to be doing from 0 to 3. Because G has a value of 250 at that point, I'm going to be using F of t minus 250. Instead of just saying minus G of t, I'm going to specify 250 on this interval. And at this point, I'm going to go ahead and plug this into Desmos to see what happens. All right, so let me get rid of this. We've got F defined, so I'm going to do 5,000 plus integral int 0 to 3. And in here, I'm going to need a parentheses, F of t minus 250, close parentheses, dt. And that's about 5,127 if I round that off. I don't have to round it off, but I'm going to be rounding off the final answer, so it's up to you when you round these things. Now for the next thing we're testing, we also have to test W of 7, the other endpoint here. So that's going to be, well, this is going to be a little bit tricky. So what I'm going to do here is I'm going to take the value I just got from W of 3, and I'm going to add to that the integral of W prime from 3 to 7. So to do that, I'm going to be doing integral 3 to 7 and F of t minus, now I'm going to use 2,000 for my G of t function, because again, that changes once I get to 3. Let me go back into the calculator and put that in now. Now I'm using this value I just got here. I'm just going to copy and paste that. So copy it, and then I'll just add to that integral from 3 to 7 of, and this time around I'm going to be doing parentheses F of t minus 2,000 dt. And that's about 4,513.14 and some change. Again, you could take it out to decimals if you want, but we're going to be rounding this at the end. So comparing all these values, the highest out of these three values is this middle one, 5,126.591. So that's 5,127 gallons then. That's going to be our max. And just to make sure we actually answered the problem, they want to know at what time that happens, so let's specify that that happens at time 3 hours. For this calculator-based problem, we're told that at time 0, a tank has 48 gallons of water, and then from 0 to 4 minutes, water flows in at a rate given by this E of t function in gallons per minute, and leaks out at the rate given by this L of t function. We want to know how many gallons of water are in the tank at time 4 minutes. Okay, so to get this, I need to take the initial quantity that was in there, 48, and I need to add to that the total change in water from 0 to 4 minutes. Now to get the total change in water, I need to take the integral from 0 to 4 of a function that gives me the overall rate of change of the water. To get the overall rate of change of the water, I just need to do the rate going in minus the rate going out. So then we're going to have integral from 0 to 4 of e of t minus L of t, rate in minus rate out. And then this is just going to be plugging it in the calculator. So going to Desmos, let me create my e of t function on here. So that's going to be 12t, sine of parentheses, let's do pi over 4, arrow out of that, and put a t in there, close the parentheses. And let's also put in our L of t function, which is going to be, let's see here, fraction 6t squared, and that's over t plus 2. And now let me just do this integral the way I set it up here. So 48 plus integral int from 0 to 4. And I'll do a parentheses and e of t minus L of t, close the parentheses, and put a dt. And that's coming out to 82.749. And that's gallons. That's going to match choice B.